Good day, everyone. You're welcome again to another edition of our STEM class. Today, we are going to take a special attention on physics. We shall be focusing our attention to the just concluded physics exam, uh, the theory parts of 2026 WAEC exam, question 3A and 3B. So the question is this: use the relationship between stress and strain relative to Hooke's law to determine the A. SI unit of Young modulus, and B, the dimension of Young modulus. So the very first thing we need to do here is to recall what the formula of Young modulus is. So Young modulus, okay, Young modulus is actually equal to tensile stress over tensile strain. So that would be stress over strain. So the tensile stress is equal to force over area. So that's the formula for tensile stress. And we all know that the unit of force is Newton and the unit of area is meter squared. So the SI unit of stress is Newton per meter squared. So then secondly, we also have the tensile strain. So the strain is extension divided by length. Extension divided by the length. So as a result, this is going to be meters over meters. That will cancel out. So strain is actually dimensionless. It has no dimensionless. So it has no dimension. So we can then conclude that Young modulus is going to have the unit of just stress because the unit of strain is dimensionless. So therefore we say the unit of the SI unit, of Young modulus will be exactly that of stress, which is Newton per meter squared. Now apart from that, we can also conclude that the SI unit of force, which happens to be in forms of Newton, can also be changed to the basic SI unit, and that will be force is equal to mass times acceleration, that is ma. So we all recall that mass is in kilogram and acceleration is in meter per second squared. So we can also conclude that the unit of stress, apart from being Newton per meter squared, will also be kilogram meter, okay, per second squared, then divided by meter squared. So we can do that. So when you do that, what are we going to get? So we have kilogram meter over second squared divided by meter squared over 1. So that gives us kilogram meter second squared multiplied by 1 over meter squared. So this and this is cancelled, and then you have kilogram per second squared per meter. So this is going to be the SI unit of Young modulus. So you can either have this as the SI unit or you have this as the SI unit. Any one of the two is actually appropriate. That is, the SI unit of Young modulus can be Newton per meter squared. It could also be kilogram per seconds per meter squared. But this is actually the basic SI unit because it simplifies the whole of the units in form of its basic forms. So the second one is actually to solve the dimension of Young modulus. So how do we get the dimension of Young modulus? So do not forget that we've actually gotten the SI unit. So we want to use the SI unit to get the dimension. So the SI unit of Young modulus, right, has been obtained to be kilogram per meter per second squared. So let's then resolve this into the dimension. So to resolve that into its dimension, our kilogram is going to have a dimension of, since it is kilogram mass, that is m, then the dimension of m, that is length, so that is L, and the dimension of S representing time, that is T. So we can resolve them now by putting the dimension into their respective position. So it will imply that this is going to be equivalent to m, then meter per meter will be equivalent to L raised to the power of minus 1, and per seconds will be equivalent to T raised to the power of minus 2. So finally, of Young modulus will therefore be equal to m L to the power of minus 1 and T to the power of minus 2. So this is the dimension of Young modulus. I hope this is understood. We meet again in the next class. Have a nice day.